from Max Planck, who will talk about long-range correlations, finite size effects, and intrinsic defects in organic semiconductors.
Thank you very much for the kind invitation. So as you will see, I'm not going to talk about nitrides on inorganic semiconductors. In fact, I was hoping that the previous speaker would introduce a bit the field, but that hasn't happened, so I quickly put some slides in to do that. So I will talk about, so I'm a theoretician, so you will see that very soon. I will not have too many equations though, so if you're interested in equations, you can come and talk to me. After the talk. Okay. In fact, I have a microphone, yeah?
No, this doesn't amplify. This is just for recording.
Oh, right, I see. Oh, I was thinking that it's going to help. Oh, okay, yeah. So if I don't talk loud enough, then wave your hand or something. All right, so organic semiconductors, for those of you who don't know what these beasts are, it's simple molecules. These are examples of these molecules shown here. They can be conjugated polymers, so this is an example of such a polymer. Can be small molecules, can be C60, buckyball. They can have some funny atoms in, not only carbon, etc. The common feature of all these molecules is that you see these double bonds in here. What it means is they are conjugated. Yeah? So conjugation means that these carbon atoms here, they are hybridized, so sp2 hybridized. That means that they have a certain orbital, electronic orbital, which is very extended and sticks out of this sticks out in the direction of the bond and perpendicular to it. So there are several of them. And those pi orbitals which stick out in the direction of the bond, they form this delocalized electronic states. We call them pi and pi star state, so occupied is pi state and the pi star is unoccupied state. And those which are sticking out here, if you have two molecules like this, those orbitals overlap very well. Yeah? So that means that you have a certain electronic coupling element, direct coupling between the close lying molecules. And that favors charge transfer from one molecule to another one because of this overlap. And because of that, these molecules can conduct electrons or holes. That's so the first thing. And then the second is this pi and pi star orbitals. They are fairly far away from each other, so the molecules have a gap, so they are optically active, so in the visible range. So obviously these materials then can be used in optical applications, and they can conduct charges. This is the examples where they have been successfully or unsuccessfully used. The most famous example, of course, is light-emitting diode, not for the lighting application, but if you have a device like this, this is basically an AMOLED display, and 3 pixels which are there, red, green, blue, are organic semiconductors. I'll come back to that later. So another, to a certain extent, niche application for organics is the solar cells. Why niche? Because inorganics has become so cheap and so efficient that there is no chance for organic solar cells to beat those. Where they could still be very useful, you can make the solar cell transparent, which is very difficult with inorganics. So you can, for example, if you have a skyscraper with the glassy windows, just cover them with the solar cells. And finally, the third very a big research area is organic field effect transistors. But I will not talk about this. I think Simone will take over and help me in this respect. So here people fight for high mobilities. Here people fight for high efficiencies. Here they fight for high efficiencies and stabilities. So that's basically the targets of the field. So we have had a very nice tour of the lab. Thank you very much. So, I mean, the responsible is not here, but never mind. So basically, you have seen that if you're working in inorganics, and as experimentalist, you have to run this big service type facilities. It's the same in organic semiconductors. You have to have first organic chemist who will synthesize the compounds for you. Secondly, you have to have a very big clean room where you prepare devices. And you have to have an army of people characterizing them. So this cycle is also fairly complicated. And this is a jog basically of the field. So that this compound was designed to actually cure HIV virus, because this thing, the C60 buckyball, was fitting the pocket of the molecule which causes the virus very well. So they thought to make this soluble, so I added this tail in here so that you can put it in the body basically. And of course it didn't work as to cure HIV viruses, but eventually it became one of the best acceptors in the solar cells. And in say 5 years ago, it was the best acceptor in the solar cell. So you see how the design of these materials works. Huh? So since I'm a theoretician, that's basically you are trying to come up with molecules like this. Maybe they will not cure HIV virus, but and basically optimize the properties of these applications starting from the chemical structures. Yeah? So our goal to a certain extent is to try from the chemical structure upscale to morphology of materials in these devices, and further to say density of states, and further to the master equation, and further to the current distributions, which are shown here. And all this preferably without fitting parameters, so that we don't rely on the experimental data, because we would like to get the feedback to the chemist, how to improve the chemical structure of the molecule. And I'll show you, I basically made an overview where I show a couple of examples from the field where this works or doesn't work. Okay, so that's a bit more in detail, the steps, and I will talk about them later in a bit more detail. So basically, what we need, of course, is the morphology. So I've seen you have extremely nice experimental input from in inorganics, where you can see the map of your distribution of the molecules in the system. The same problem exists in organics. You need to know how molecules are packed with multi-component mixtures, how they orient, etc. So you need to predict atomistic morphology if you are serious about studying properties later. From here, you have to go to electronic processes happening here, and these are electron transfer, hole transfer, exciton transfer, creation, annihilation, etc. So it's all very similar processes which you have, except we are, in most cases, dealing with the localized by default states. Huh? So there's this electronic excitations here are fairly localized. Materials are disordered or reasonably ordered, and therefore we don't need to localize them by the composition or something like this. So what we do normally is we again use Fermi's golden rule on this morphologies. In Fermi's golden rule, you have electronic coupling elements, so that we calculate using quantum chemical techniques. In Fermi's golden rule, there is an energy conservation, so you need to know the particular ionization energy or electron affinity of electron or a hole in this morphology, so in a solid state. So to calculate those, we use a perturbative approach with the polarizable force fields. And then once we know this too, sometimes we can also calculate phonon spectra. We can integrate the Fermi's golden rule, calculate the corresponding rates for the charge transfer or exciton transfer, and write down a master equation where all these processes are listed out, solve this master equation, and get the currents. So that's the typical workflow we would follow when studying these systems. This is all lots of work that has been implemented also in a software package. So in principle, if you're feeling like studying one of the systems and you would like to visit us and learn any of these steps, you're welcome. All right, so then a very quick example how it works. So here are typical host materials. So these are not molecules which are, of course, in that OLED, because these are public molecules. There is one molecule in there which Merck develops, and we don't know the structure of that molecule. But basically, it looks like one of these. Huh? And in an OLED, you have amorphous morphology of this molecule, so it's fairly easy to simulate the amorphous morphologies. So if we follow this pathway, which I've just described you, simulate the amorphous morphologies of 2,000, 4,000, 5,000 molecules like this, calculate the site energies using polarizable force fields, calculate the electron coupling elements using quantum chemistry methods, calculate the rates. What we will end up with is fairly coarse-grained parameters. It's ionization energies, which you can compare to experiments, for example, ionization energies for holes, and widths of the density of states. So in this disordered materials, density of states is very often Gaussian, and that you can fit it easily with the Gaussian distribution in this case. And you see that the values we are getting, which were determined experimentally and from simulations, are in a fairly good agreement, even for ionization energies, which is very often not the case. Huh? And once you have done this, you can also solve the master equation and simulate IV curves. So I show you two examples here for 2T nata and 2T CTA. And you see that the accuracy we can get without actually doing any approximations in here. So that's works very well for these systems. Yeah, so that's an advertisement, how ideally it works. Now I will talk about problems. So that's there's no problem, you see. Like I could stop here if it had been working. Yeah, sure. Yeah. There are many problems. So of course, first thing what I've done is I picked those compounds which I liked in the previous slide. Yeah? So that's how everyone does. The special about them was that there was no large dipole moment of the molecule, and in this field of organic semiconductors, it's known that if you have a large dipole moment and you make an amorphous morphology, there will be a large fluctuation of the electrostatic potential in your morphology, and therefore electron will be moving in a very disordered energetic environment, a very disordered potential. And that means that since we are doing simulations with small systems, eventually we'll have problems with the sort of finite size effect problems. And I guess in nitrides, you will also hit that problem at some point. Yeah? So you're already on the way of calculating the rates. So you'll realize if your energetic disorder is of the widths of the, we call it localization potential, is around 0.14 eV and more, you're in trouble. So I can already promise you this. So where the problem lies from? So where it is? So it's very easy to explain, and we have noticed it by chance. Since we were very pedantic, we said, okay, let's take a box of this amorphous material and see whether we do have finite size effects. So let's look at boxes of 500 molecules, 2,000 molecules, etc. And that's at that time was maximum we could do with this technique. And what we looked at is after solving the master equation, you come up with the mobility, and I plotted as a square root of 1/2. I apologize that it's not dimensionless, but that's how it's normally presented in experimental papers. So since I have experimental line in here, I did it. I committed the crime as well. So, and as you can see here, that's the smallest system, 512 molecules. This is 2,000 molecules. This is 4,000. This is 13,000. And the problem is that it doesn't seem to converge. I mean, it just goes down and down and down. So we have quickly realized what the problem is, and to realize basically what the problem is, what we have done is we calculated the average energy of electron in the system. So we know that if you have a Gaussian density of states, an ideal system, everyone loves that, then the average energy of the electron is just the width of this Gaussian divided by kT, or sigma squared divided by kT. And we can evaluate this in our morphology by just taking a mean of this distribution of the energies. So we have done this, and that's the results of, let me explain you in a bit more in detail. So these points are simulations of this average energy as a function of the number of molecules we have in the box. And these three lines are given for different sigmas, so different widths of the Gaussians. And what you can see is that if you have a small disorder around here, then your average energy practically lies on top of the one which infinite system has. Once you are having a larger disorder, so a broader Gaussian, you see that especially for small system, you have a very strong deviation. And if you go to this sigma over kT 5.4, that's the experimental value we had for that compound, you see that in principle, we are going to hit this somewhere here. And if you look at the logarithmic scale in here, that would happen at around like probably Avogadro number. Yeah? So that's no way we can simulate that. And you can run a very simple arguments of where this point is that your asymptotic behavior starts approaching the infinite energy value, and you will see that the dependence is very simple. It's logarithmic in the number of molecules, and that means that you're fighting against exponent, which is always a lose. There's no win-win situation here. So basically it tells you that whatever mobility you're going to simulate is going to be wrong because you are running your system at a higher energy. And the reason for that is very simple. If you have a small simulation box and you have a Gaussian distribution of density of states, your tails are gone. So you lost your tails because of your sampling over n molecules, not infinite number of molecules. And transport of one single electron, it does occur in the tail. So it's sensitive to what happens in the tail. Since you lost it, you're making a mistake. So of course, we worked with experimentalists at that point, and they say, well, it's not a nice situation. Yeah, we are looking at macroscopically large systems, and where you're giving us mobility in a 500 molecules box. Not good. So we've looked again at this equation, and actually this has also a solution to it. Well, it's a semi-solution. If you look at it, this threshold, when you actually start hitting the line where you would like to be, is very sensitive to the width of the Gaussian and temperature. So there's the dimensionless constant in here, sigma divided by kT, and it tells you that this transition is given by can be moved towards the left in number of sites if you just increase the temperature. So what you can do is you can do fake simulations where you have morphology and everything else rates evaluated at room temperature where you're interested in, but then you run the kinetic Monte Carlo simulations at much higher temperatures. So in this case, we had to do like 10,000 Kelvin now to get to the regime where you have. So I mean, it's obviously senseless simulations, but if you want to extrapolate from these simulations back to the room temperature, you need to know, of course, how mobility depends on temperature. Luckily for us, there was an analytical expression for one-dimensional case given, and we have checked that it reasonably well reproduces also the situation in 3 dimensions. So this is plotted in here. So you see for all these 4 box sizes, which I have shown to you, we did simulations at very high temperatures, up to 50,000 K. And then we used this expression to scale basically everything on one line and extrapolate it to room temperatures.
How was that expression obtained?
So there is exact analytical solution for 1D. Derrida derived that. Maybe somebody did it before, but I know the paper of Derrida. Yeah? So, which tells you if you know all the rates, all the hopping rates in 1D, then you get the diffusion constant and mobility immediately. Yeah? So that's and that comes from there. So it assumes also the functional form of the rate of the temperature dependence of the rate. But that's exactly the one we used, so we're playing on the safe side. So if you do this extrapolation, that what happens is that all these curves collapse on. So basically, at these 2 points, we cannot do it at large fields, only at small fields, because this expression works only for zero field. You see that they all collapse here, and you see how basically the difference is 10 to the minus 6 to 10 to the minus 9, just because of the finite size effects. And this is the experimental value of the mobility which you find in the literature. So that's the first thing which we have to be very careful when you're doing simulations, especially if you know that you have a large disorder in the system. So I can tell you that all these problems start to show up when your Gaussian density of states width is about 0.1 eV and higher. If you have sigma which is smaller than that, it is no problem. You can use very small box sizes. All right, so then what you can do then is also do IV simulations, and you see that again it works very well for high temperatures, and then here you start again heating the problem that at low temperatures you cannot even do an extrapolation very well. Yeah, so that already doesn't work. So, but luckily enough, nobody is interested in using OLED at minus 100 degrees. So, well, okay. So that's basically all what I want to tell you about the finite size effect story. Maybe there are questions, and I'll be happy to get rid of it. Okay, good. So basically, what I have just told you is that what we can do is. Or we could do is to calculate the density of states from sort of first principles. So without relying only on the chemical structures and the amorphous morphologies. And we have done that. Of course, we were very happy that we can do that, because that means that we can indeed predict mobilities, etc. In these materials. And we have done it for 50, 70 compounds. And we have noticed that this is a subset of these compounds where experimentalists explicitly complain that it's wrong. And the subset was those compounds where we would say that our sigma is big. So we could predict our sigmas, so the width of the density of states, of the order 0.3, 0.25. And experimentalists would never see that when they would perform SCLC measurements. And that somehow was always, we couldn't understand why that is the case until we realized that there was some very important ingredient missing, which we didn't take into account because we worked always with the pure systems. So to explain you a bit experimental data, which I'll show you later, I have to tell you a bit about this space charge limited current measurements. So basically what you do is you measure IV characteristics and in a simple diode geometry. And once you know that your IV curve falls on the approximately V squared dependence, actually exactly V squared dependence, you tell that, and you don't have injection problem, etc., you immediately know that you're in this CLC regime. And if the slope is 2, then you also know that there is no trapping in your system. So this is just information for you to believe, but you can look up the corresponding derivation. That's the case. So, for example, for this compound, ICBA here, you have an ideal transport, no traps in the system. If you look at PCBM, So these compounds which are supposed to cure cancer, you see that it's already deviating from V squared, so there's a bit of a trapping inside. If you look at C60, there's a very large deviation, so this really is trapping the carriers, which is very surprising because C60 is a very neutral molecule. It's basically has no dipole moment, nothing. Why would it trap carriers? That was a big puzzle, the same as PCBM. And what we have realized is that if you do it if you have a good PhD student who can do it for this number of compounds, and he plots the slope of this curve as a function of the ionization energy or electron affinity here, you will see that there is clearly two kind of universal cutoffs for electron affinity around 3.5 eV and for ionization energy around 6 eV. So everything which is in this window is trap-free. Everything which is in this regime has problems, so it has traps. And of course, what we have been doing in our calculations, we have looked at all these compounds also in a situation where they should not have traps, like C60, because it was a pure system which we have looked at. But with the help of this plot, we have realized that there is a universal something in the system which brings these trap levels there. What can it be? I mean, you have a clean room, right? You have also nitrogen atmosphere there. That's for a reason. It's probably either water or oxygen. So it must be something universal, yeah. So unfortunately, water and oxygen, they don't have ionization energy of 6, for example. It's much deeper. It's around 12 eV. But if you have a pocket where you can collect a few water molecules, a few water molecule has a strong dipole moment. So if you put a charge on this water molecule, the surrounding shell of molecules will reorient and stabilize that charge. And by that, you lower down the ionization energy of this complex to 6 eV, around 6 eV. So that is a universal trap you can have in your system. So here is an example of the densities of states of this system. So here's in this yellow is the C60 density of state, as we would calculate in the pure system. Then you mix in the water, and you see this violet things is those pockets where we have stabilized by H2O cations. And you see they serve as traps for the density of states in here. And of course, that we couldn't take into account. We would just simulate the system as such. You cannot get rid of this trap. The density of this water in the system is so low that it cannot be even detected in using analytical techniques. So IV characteristics see that, but you cannot detect it otherwise. You can heat your system, they just stay in there. There's nothing happens. Yeah. This is water, yeah. So
the solvent is water, or is there something else?
How the system was processed experimentally.
Or is this a solvent? I mean, is it frozen?
This already is an amorphous morphology, and in simulations we could put in the pockets, which were inside, a bit of water.
Right, but no, but I mean, when you process, I mean, when you
yes,
the
there's a polar solvent, non-polar solvent. People have tried lots of things. People also try to neutralize this water by filling pockets. It helps a bit, but there is always something staying inside. So that is the reason why you have basically the 6 electron volt cutoff, where you start seeing the problems with the transport. Huh? Yep.
I'm confused. For your previous slide, you showed the two regimes. Is this
6. I'm talking now about this one. Huh?
Yeah, right. Is this simulation or is it experiment?
This is experiment. You can trust this one. I would be more skeptical about this one. Yeah. So this is solid data. It's not going to change.
You're trusting experimentalists?
I mean, when there is enough statistics, I do. Huh?
Okay, sure.
There's pretty good statistics in here. So about electrons, the reason for them, or people already knew before us. So they knew that oxygen, when stabilized by water, can lead to such a trap of the density of states for the electrons, so it will be somewhere here. So that has been known. So you see the oxygen and water are always there. You cannot get rid of them. And if you would like to simulate your devices from first principles, you cannot do it without taking into account that you have these intrinsic defects in your system. No. So that's kind of, I don't know how it is in nitrides, how deep you are, and how shallow is your electron affinity, but maybe it's something to pay attention to as well. Okay, so that's the end of the second story. Any questions? No, good. So everything is just clear. So then I'll change to a topic slightly. I'll talk about long-range effects. So it's probably the most related to localization you're observing. So that's what we also kind of see. Or maybe you have some correlations with what you potentially could see in your systems. So to explain you further, I'll just tell you a bit how we calculate actually this density of states. So as I told you, it's a perturbative approach. So we start with the gas phase. So we have our morphology. We pick one molecule. We do gas phase calculations. You pick your method of choice, or you pick it according to the size of the computer you have. We determine the gas phase electron affinity, ionization potential. And then we take into account perturbatively effect of the electrostatics. So basically static electrostatic multiples sitting on the molecules around. And then at the second step, we take into account the polarization effects, so induction, which sits on your molecule. So it's done with a toll model, and we develop force field for every specific compound from scratch. And what happens then your gas phase levels can go up or down depending on how the electrostatic potential is distributed in here. And if you switch on the induction, then you know that your gap always narrows, so because it stabilizes the system. And that's the solid state ionization energy electron affinity, and that's what we are interested in. And we had a different project than the amorphous systems. It's a solar cell based project. And in solar cells, people look at a specific class of molecules even without knowing that they're working with specific class of molecules. If you look at the publications, always the same molecules. And this is ADA type, so-called. So acceptor, donor, acceptor type molecules. Electron rich part, electron rich part, electron deficient part. So here's plus, here's two minuses. So you have two strong dipole moments which cancel each other. So this molecule has a quadrupole moment as the first multiple, electrostatic multiple. Same with this molecule. By symmetry, it has only the quadrupole as the first electrostatic multiple. This one has a dipole, but in the solar cell, they are all packed nicely. And if you look at the packing, there are pairs of these two molecules in the opposite direction. So the dipole moments cancel. So all these molecules turned out have quadrupole moments as the first electrostatic moment, active electrostatic moment. Surprisingly, there's a reason for that, of course. Let's have a look now how this perturbative scheme is going to work, because I told you this. In the first step, we have to calculate electrostatic potential. So you have to calculate how charge, this is charge, interacts with the quadrupole moment of the neighboring molecule. This we know at large distances is roughly charge multiplied by quadrupole moment divided by r cubed. So this is the important part, it's r cubed. So it's nothing else as expansion of Coulomb law. And now if you put more molecules around it, you will have to integrate over volume. And then pleasant thing, this is a log. Diverges. So the Madelung was the person who realized it quite long ago. So there's this, if you do it more accurately with the sum instead of the integral, because this is an approximation, of course, you will notice that the sum can be conditionally convergent. So depending on how you do the summation, you will get different answers. Well, yeah, why not? It's a sum. So for most physical situations, that doesn't happen, luckily. But what happens is that since there is a very large, pretty strong divergence here, your sum becomes sensitive to the shape, macroscopic shape of your system, which is a very dangerous thing. So now value of the ionization energy of the charge which sits in here depends whether it's a cube, a sphere, a thin slab, or something else. So that's not good if you're doing experiments. So, okay, so here's the implication on this for solar cells. Solar cells are made like this. You have so it's not a real solar cell. It's a planar junction solar cell, so inefficient solar cell. You have two layers. One is donor, one is acceptor. And now if you put a charge somewhere here, and we start doing calculations as we used to, so basically truncating the cutoff at certain distance, and we push the cutoff further and further, what we will see is, for example, for the cation, at some distance of 16 to 20 nanometers in this case, we will get a saturation. And normally we would just stop in here because this is computationally extremely demanding. A 16 nanometer system with 32 basically, even with polarizable force fields, it's challenging. And if you stop in here and you didn't take into account that the shape of your system is not a sphere, but actually a thin film, you lost minus 0.7 eV because this system will go here. So it will be somewhere here. And the convergence will be around 100 nanometers. So that's what this long-range Coulomb electrostatics does to you. And yeah, I mean, I had previously a slide here with the papers which didn't take this into account, and I took it off because I didn't make friends by putting that slide in. So, but there are a number of people who made that mistake and took this energy levels instead of this energy level. All right, so we had to work a bit on development of technique which could make this efficient. I don't have time to talk about this. The direct verification of this technique is, of course, UPS measurements. So they work with thin films of this organic semiconductor, and they measure ionization energies and inverse for the emission spectroscopy electron affinities. And that's what we can calculate. So basically, we have done this for a series of compounds. This black lines is experimental data. You can have different orientations of the molecules in the film, so they can be standing up, lying flat, etc. So that's why you have different numbers for the same compound. And in blue, our calculations. So you see that from our calculations, we can even tell how the molecules are sitting in the field. And that takes into account this crystal field with the geometry. If we would not do this, we would be off by 1 to 2 EVs. Okay. That actually creates we haven't realized that at that point, but later on we realized that this is a very neat way then of controlling the crystal field inside the organic semiconductor. Because what you can do is you can have molecules which are very similar but with very different quadrupole moment. If you fluorinate this molecule, you change the distribution of charges to the extent that this has a negative quadrupole moment and this has a positive quadrupole moment. But still they crystallize in the same crystal structure because their van der Waals interactions are very similar still. So that's basically the crystal structure, and what you have done is a composition. So if you now change the composition in this crystal, what you will see, and you put a charge inside, this charge basically will average over the entire environment, and therefore you can change ionization energy by changing just the composition. So it's a very simple physical way of changing ionization energy or electron affinity without modifying the chemical structure, which is pretty nice. I mean, it's nice to the extent that we could actually sell this to science by rediscovering nothing else but Coulomb law. So, yeah. And that's the experimental validation. So you make these mixtures of zinc thalassine and a fluorinated zinc thalassine, and you measure the ionization energy as a function of the concentration of one of the components, and you see there is a continuous change of the ionization energy by 1 eV. So that's how much you can vary the ionization energy. You can even do more if you take if you do more fluorination. And that, of course, is very nice because in all these devices, you have to tweak energy level alignment. For solar cell, you have to have a specific alignment of ionization energy, electron affinity, etc. And that allows you a very simple way of doing it. So without going to a chemist and saying, well, can you halogenate and on that side? Yeah? And it had a bit more implication, in fact. And I don't think I will have time to talk about this. Huh?
5 minutes.
So basically, a big puzzle. I'll tell you the problem. You might be interested in the problem. So the big problem in the organic photovoltaics is why this so-called charge transfer state splits. So what happens in the organic solar cell is that your dye molecule absorbs light, and you create an exciton. This exciton can, via energy transfer, diffuse towards the interface. And this interface is designed in a way that there's a donor and acceptor molecule, so it can split this exciton. So you separate now electron and hole a bit further, and therefore a Coulomb binding is significantly reduced as compared to the exciton Coulomb binding. But if you calculate how much this, I don't have that slide, so if I can calculate how much this binding is, it's still much more than kT. So it's about 10 kT. So in principle, if you don't start thinking about delocalization effect, so like more sophisticated things than just well, solving simple Schrodinger equation. So then you cannot come up with the explanation why the CT state splits. The energy is the binding energy is too strong. And basically what we have shown is that because of this funny electrostatic effects at the interface, we have if you have a bit of a disorder, for example, one molecule sticks out into the so let's say this is the acceptor, it sticks out in the donor, then the dressing, electrostatic dressing for this molecule will come from this phase, not from this phase. And that changes the energy levels of your CT state enough to reduce the binding energy to kT. So basically this rough interface plus this electrostatic forces leads to splitting of the CT states. And that also relates to the quadrupole nature of the molecules, because you have to have a very specific sign of the quadrupole and alignment of the molecule at the interface to do that. And that's why they also have, most of them have ADA structure, because if you do DAD structure, this is the wrong orientation of the quadrupole moment. All right, anyway, so I will skip this. And I had one more section, but I think I will be happy to answer questions.
You said if you're willing to do something beyond DFT to compute the exciton, the charge operation, I guess, you mean something like Bendel-Salpeter or?
That was there was something on the menu for the evening, and it was So in principle, we can do BSE. Indeed, it's a QMMM type. BSE calculations where polarizable force field induces a self-consistent QMMM where polarizable force field induces electrostatic potential, and then we cast that exciton on multiples and propagate the electrostatic field to outside, self-consistently converge induced dipoles, and that goes until you are happy.
Denis, I have a question to the separation at the interface.
Mm-hmm.
In old idea of architecture, the dipoles of the interface squeeze the hole and just increase kinetic energy. Your explanation is alternative, or you have an argument against the model?
I don't have an argument against anyone at the moment.
No. That's there or not?
No, so the idea.
Not anyone, but against the model.
No, the idea here is very simple. It tells you the following. You have to calculate the energy of a charge transfer state at a rough interface. Once you do that, you don't have binding energy of 0.3 eV. You get I have a plot in here, in fact, I can just show you.
There's no problem, you say.
So then CT state it can be split just because of the electrostatic potential built at this
So you don't need
interface.
that.
Then you don't need that, yes.
Can I step up another disagreement?
Yes, sure, yeah. I mean, I knew that you're going to ask a question.
We measured that Coulomb binding energy,
Yeah,
and it is 0.3 volts.
yeah. How do you do this?
We measure it by measuring the Stark shift, or the electroabsorption, between the separating electron and hole using transient optical spectroscopy. The Stark shift is quadratic in electric fields, so we measure experimentally, it was on my slide yesterday evening, we measure the volume integral of the square of the electric field, and all we have to do is multiply it by half epsilon, and we have the Coulomb energy in absolute units. And we've done this systematically. Every time we find that the Coulomb energy, by the time the electrons and holes are separated, is at least 200 millivolts in all cases.
So
We don't think there's a problem. There are mechanisms by which.
yeah, you can. Yeah, I know alternatives. I mean, there's a slide with all possible
Yeah.
delocalization, entropy, and people came up with lots of things. Huh?
So I don't think we want to explain away and pretend there isn't a Coulomb energy. It's quite easy to measure.
I see. So I will have to have a look at how the measurements are done. So that's. It's not that I'm saying that I don't believe that you're doing the right thing. Don't get me wrong. But well, for example, very often, for example, if you tell me ionization energy in your system is 6.5 eV, and I plug it into the density of states I'm using, you were using onset, for example, of your density of states?
This is very straightforward. If you look at the transient optical signal
Yeah.
through the sample, what you see is a derivative signal of the optical absorption of the material between the electron and hole. You can separate it out as the Stark shift. It arises because there is electric field, and it's quite a high field, and you can normalize it by doing a CW electroabsorption measurement, and it turns out that almost trivially what you measure is the Coulomb energy in electron volts, and it is large.
Let me talk to you after this session. Yes, I'm curious about this. I mean, I'm not doing anything exotic in here.
And if I can give you a less fundamental
Yeah.
objection, when we time the charge separation, it is ultra fast. It happens within a picosecond. So it happens everywhere, not at preferred little bumps on the interface.
Yes, so that I can. Okay, yes, yeah, I see. So this objection I can I accept. I also know that there's a certain part of the excited states which is dead, which of CT states which is dead, which is not producing charge-separated
But
state.
the fact is only 200 or 300 millivolts is already interesting. It does mean that there has been some charge spreading, that the electron-hole pair is already somewhat delocalized. You would otherwise expect it to be even larger.
So here there is not delocalization. Yeah, that's by default we assume a localization on a molecule. Yeah, so we haven't taken that into account. But that's already enough to have a zero offset for the charge separation. Yeah, okay, I think that I'll be happy to talk to you after the session, definitely. There are several camps in explanations of why CT state splits. So.